parameters, which are the
recording in progress,
the gamma parameter and the experimental resolution. So after that we have coordination numbers. So for coordination number, first you need to define how many you want to use. So this is done again to try to minimize the number of parameters you need to fit. So like for example, in the case of crystal, you maybe already know that your system is FCC, and you already know that all your coordination number, then you can only define one parameter and define all other coordination number for other shells based on that as a multiple of that unique parameter. So you don't need to fit more than one. So in this case, we'll use only one parameter.
Fabio, slightly to interrupt. Which file is this one actually?
This one is this fit ccln.in.
Okay. Yeah. Thank you.
Which is the input file for video. Yeah. I don't know how you called your folder, but so if you copied before, so it's inside this.
So this is the same file where you were talking about the broadening and all the other aspects like gamma and the EB aspects of this actually.
Yeah.
Okay.
Okay. So yeah, the file that we saw before leaving this this morning. Yeah. So okay. So as I was saying, this is how many coordination number we use. In this case, we use one, and then we need to give the parameter number for this coordination number parameter. So in this case, it's 52 because if we go up in the initial table, we see here this 52. It's coordination number, and it's 4. So if you see, in this case again, we know it's a small molecule with 5 atoms, so we don't need to fit the coordination number because we know it. So in this case, we put 4, and here in the interval for searching, we put 0. So what this means is that this parameter is not fitted, is kept fixed. Okay, then we need to define how many numbers of 2-body and 3-body peaks we want to use for fitting. So here we have one, if you remember before, we calculated we only have one 2-body and one 3-body. So here we put 1, and then we have to decide what kind of peak we want to fit. So usually for 2-body there are 2 possibilities, either Gaussian peaks, which is given by this G, or we can use a gamma-like function, which are kind of asymmetric Gaussian, distorted Gaussian, let's say. And what it changes is the number of parameters that are required to fit. Let me look. So here again, if you look in the manual, everything is written more details. But yeah, this one. So 3 models. Yeah. So G, as I said, it's a standard Gaussian. E, it's a gamma-like distribution, and C, it's another possibility, which is so-called the cumulant expansion. Maybe it's another way of expanding the two-body signal. So let me go back. So in this case, we do Gaussian. So for Gaussian, we need two parameters, which are
Fabio?
yeah.
By asymmetric kind of Gaussian, do you actually mean it's Gaussian Lorentzian convolution? It's basically do you mean a fork function here?
I don't remember. I think the function is written. It's written somewhere if in the manual.
I see. Okay.
So in that case, we have. Wait, maybe I will find it. Okay, this is for free body. Okay, let me do. No.
So
Yes, this one. Yeah, it's this one. Yeah, so it's kind of complicated function, but basically it's like distorted Gaussian, where this beta parameter gives you the how much is distorted.
So this distortion is limited to some particular energy edge, or is the distortion like the lower edge is distorted, or the strength of distortion like asymmetry?
No, this is for the the structural refinement.
Okay.
So it's for basically in our case the molecule to describe the two-body distribution function.
Okay.
So what? Wait, I have. So I will talk later, but the first slide that I showed is one that also Andrea showed this morning. So the pair distribution function for a system, it's described by these peaks, no? If you have a crystal system. So basically that these peaks usually, okay, for crystal you can use the Gaussian function, this is our Gaussian, but for high temperature or disordered system, you need it, you see it's highly distorted, so we use this gamma distribution. So this gamma is like these peaks you see under here, which how to say dashed lines. These are the function that we use to fit. So yeah, so this is what these functions are. So for pair distribution for two body, it's easy to visualize. For three bodies, more difficult, but the idea is the same. So because we use Gaussian, we need two parameters. So it's the average distance, so the center of the Gaussian, and the sigma square. So let's call this Debye-Waller-like function factor. And again, here we put 15 and 16, which are the parameters here, the numbers here. So 15, this is the distance, and 16 is the sigma square. So we can put some initial guess and then let it change. Okay, then, okay, this is for the parameters. Then, so again, we have to give how many signals we want to use to fit. So, as Andrea explained, the parameters that are used to fit all the multiple scattering expansion that we calculated before using GNXAS, and we can use either use this Xi2, Xi4. These are the single multiple scattering expansion, or we can use the total two-body signals. Let me go and show you again what we calculated before. So if you remember before, we calculated all these signals, and so how to read this is, okay, this is the name that we gave in the input file. Then G2 stands for the two-body peaks. So you have either this G2 dot there, this is the total two-body, or you have this G2 X2, which are the single. In this case, this is the single scattering, then the double scattering, triple scattering in the multiple scattering expansion. And for free body is the same. We have this free P1G, which is the total free body, or we can have the single multiple scattering with different parts. So when we fit, we can use we can either use the single multiple scattering or the total ones. It's the same. Let me go back to. So in this sorry. So in this point, in this case, we use the single multiple scattering expansion. So we want to put all the single scattering, double scattering, and triple scattering. So we put a total of 3 signals. And for each one, we have to give the name, the file of that derivative calculated with GNXAS. And then we have to give 2 numbers, which are the corresponding coordination number. So in this case, this is a bit, sometimes it's a bit confusing, because here we have to give the number of coordination number that we have given before, but this is just, let's say, numerical order. So in this case, we have defined only 1 coordination number, so we have only 1. But suppose, I don't know why it was done like this, but suppose we use 2 different coordination number, okay? So 2, so the first one is 34 and the second one is 52. If we want to use the first coordination number, so this 34, we have to put 1. If we want to use 52, we have to put 2. It's just in numerical order. It's a bit confusing, but as its logic. So, yeah, go back. So in this case, we have only 1 coordination number, so we will put always 1 here. And then here you can have a multiplication factor. So as I was saying before, if you want to use like only 1 coordination number parameter, then you can use instead of, for example, in this case we have 4. If we have a signal which has a degeneracies of 8, we can just multiply by 2, or we can multiply by 0.5 to have a coordination number of 2, etc. Okay, but in this case we just leave 1. Then we do the same for the second one and the third one. So this is all the same. Okay, and this is for the so all this part is for the two body signal. If we have more than one two body, we have to repeat all these parts for another signal. Then we have the free body ones. Also in this case we have only one, and also here we put this G. Again, if we look at the manual, there are we have different possibilities. G3, so we have standard Gaussian function with G, or we can have also here this cumulant expansion. And then we have a set of parameters. So in this case, for free body is much more complicated because we have two distances and the angles. Plus we have the correlation matrix. I think Andrea explained this morning. Yes, this one. So we have this correlation matrix, which gives you maybe basically the thermal vibration in all directions, and also the correlation between the different parameters. So in this case, on the diagonal, we have the simple Debye-Waller-like factor for the R1, R2, and theta. And then on the off diagonals, we have the correlation between the parameters. And we need to define all of this. Of course, if we have particular symmetries, like as is usual, for example, in our case, the free body R1 is equal R2. So we can use only one parameter for these diagonal elements for R1 and R2, but also we can use only one parameter for R1 theta and R2 theta because they are the same. So for special geometries, we can reduce the number of parameters required. And also in this case, another useful property of this program is that because our R1 and R2 in the free body distribution, so in the free body, configuration, are the same of the two body, because it's the silicon and chlorine distance, we can use the same parameter. So here, the first two parameters are R1 and R2. So if you see here, it's 15 and 15, which is the same that we used here, because that is the same physical distance, the distance between silicon and chlorine. So we can use one same parameter for different signals, which is this distance. Then, I have a delay because then we have 51, which I think is the theta, the angle, this one. These are the first three parameters. Then we have 16, and 16, as you can see here, it's the sigma square of R1. Then you have this 34, which is the sigma square or rho between R1 and R2. This actually, I think maybe it's written in the manual. Yeah, the fitting parameter used by video actually are this one. So in this case, the diagonal elements are the thermal broadening of these parameters, but for the off diagonal elements, these are scaled. So these rho actually they are defined in this range. So in this case, because it's it's easier to understand by humans how to decide the initial value of these parameters. So in case these parameters are totally uncorrelated, this will be 0. And in case they are positive correlated or negative correlated, this will be goes towards -1 or to 1. So so in this table, this rho 1, 2 is it's the correlation between R1 and R2. So it's always between, you see here, between in this case we put between minus 0.85 and 0.85. And then the other parameter correlation is this one, which is between the R1 and R2 and the angle. And again, we use the same how to say range for fitting. Of course, we have to repeat this one both for R1 and R2. So here we have so this 34 was the correlation between R1 and R2. Then this was between R1 and the angle. Then we have again sigma R2. So if you remember, sigma R2 is the same as sigma R1, so again 16. Then we have the correlation rho R2 and theta. Again, it's the same as R1 and theta, so we use the same parameter. And the last one, we have sigma of theta. So sigma of theta, it's this one. So the broadening of the angle. Okay. Once we have all this, then again, as before, we can put many different signals, or we can use the total free body signal. So in this case, if we use the single scattering terms, actually it's a bit more complicated. So you see here there are different multiplication factor, because if you calculated the degeneracy of the paths, it's not the same of the degeneracy of the free body. So these are taken into account if you use the total free body, but if you use the single scattering paths, you need to take into account the right degeneracy, which can change depending on the path you use. Okay. For body we didn't put anything, so just put 0. And next two are very important parameters that are required for fitting GNXAS. So first one is A0. A0 is the energy of the theoretical scale. One problem is that when we do the theoretical calculation by Fudge and by GNXAS, the energy starts from the Fermi energy. And so we calculate the photoelectron wave vector starting from this Fermi energy. Then experimentally, we instead calculate the K vector starting from the edge energy of the experiment. And these two quantities are not the same. So there is some electron volt of difference, and but it's not possible to know a priori how much is this difference. And also sometimes, experimental data, they can, in different beamlines, can have slightly different value of energy because of how the beamline is being calibrated. If it's not calibrated perfectly, maybe there is some slightly shift. So this A0 parameter is just the, where to put the initial energy of the theoretical calculation. In general, this should be around the edge energy plus 2 or 3 electron volt. That is a good starting value. And then you can just search around that interval. Then the next parameter which is important is the S0 square. So S0 square is the, the many body reduction factor. And this comes from the fact that when we calculate the theoretical signal, we are doing, one electron approximation, so only one electron gets excited. But there is some small reduction due to the multiple electron excitation. So actually the amplitude is slightly, for this reason, the amplitude actually is slightly reduced. So there is also this S0 square parameter that is used to fit. Maybe you have seen it in other programs also. And but this value usually around 0.9. It's very close to 1. Sometimes can be 0.7 depending on the system, but okay. And okay, so these two parameters are given here. So first H0 and then S0 square. Then this part is for the Fourier transform. If we want to do Fourier transform, we say yes. Or you can use also S because it's C in Italian. But okay, you can use also yes. And this is the parameter for the Fourier transform. So this is the K range, and this is the weight of the K weight of the signal. Okay, then this parameter is just for plot purposes. So wait, if I remember correctly, we should put 8, not 7, because yeah, we should put 8. Let me check to be sure. This is because okay, there are various levels of output files that can be created, and so if you put 5, 6, 7 graphical performances of top drawer, 8, 9, and it creates output files for new plot. So yeah, so here put 8. Okay, next one is not important. Then here you can leave just 0. This is how to say, for the standard deviation of the raw data. So it's the standard deviation of your noise. But if you don't know it, you can just put 0, and then there is some algorithm that estimates the noise automatically. And the next card is the energy from which to start calculating the noise. You can just put also here 0 and start from the initial point in the data. Okay. The last ones. Yeah, this is for statistical purposes. It's a bit long to explain, so you can just leave all yes. Then, okay, last one, also it's a bit complicated, so let me just modify this. So these are, how to say, command files that of this old CERN library that we use. But basically, is set error def is to define the the minimal error that we want to reach. So you can put like 1 to the minus 10, and then there are various commands to perform the fix. The simplest one is called the simplex, and then you give the number of steps that you want to do to minimize. So we can try to 5,000 steps, and then we should put exit. So for now, I will not explain, but there are other options that one can use. For example, you can fix some parameter also here, and then you can release them. You can do more, how to say, complicated features. And then you can also study the correlation between parameters with these contours. This is more complicated. It will take too much time to explain, so I will skip it. But okay, important point, you should put this, error def, simplex, 5,000, and then put exit. So then it doesn't matter that there is other things written, because okay, exit, the program stops.
Fabio?
Yeah.
So in the file itself there is a parameter called MFP, which I understand as mean free path of electron.
Yes.
So that appears to be 0. Could you comment on that aspect, please?
Yeah. So as I said before, in our calculation we use the complex potential.
Okay.
So when you use the complex potential, the mean free path effects are already taken into account.
Okay.
So you don't need to put a parameter. But in the case that you use a real potential, then you need to put mean free path parameters.
As a
Then there are There is also the possibility to refine the mean free path around some model, some linear model, some more complicated stuff. But in general, what I suggest you is just to use complex potential, and that is accurate enough.
Okay, thanks.
Okay, so okay, I hope everyone changed this one. Then we can save and quit and try to run it. So as I said, the program is video, So if we do video, left arrow and name of the file, and we run it, yeah, we will do this minimization procedure, and then it will stop at a certain point. So these are all the files that have been created. So just to see a few. So in general, this dot file can be seen with the top drawer program. Let me see if it works. Maybe it works. Will take some time for me, but maybe it works. Probably on your computer is faster because of the ping. Can you see it on your computer? Yeah, it takes a lot to load.
So I'm not sure we have the TD.
Yes, last, so there is a question in the chat. So last command line is this TD.
Yeah, it works, yes.
Yeah. Before TD, okay, I will close because I don't think I can. Yeah. So unfortunately, it takes too much to load from here. So the command before TD was this one. Yeah. So it's video and left arrow and the name of the input file. Okay. So so probably you can see on your computer now from remote it takes too much time because of the latency, but so there are various files that can be seen with top drawer. So PA is just the GNXAS and PF is the Fourier Transform. PT shows you the n-body expansion of the fitting, and the PX show you the multiple scattering expansion of the fitting. So all the various signals that we put. So various level of details of the fitting. Then PA is for the background. It shows you the background, and P1 shows you how it chooses the energy edge and the position of the energy edge. And then there is PS. PS shows you the estimated noise. I will try to show you PS because there is something important that I want to say. Maybe, hopefully, okay, I can do it. In the meantime, the other output files are the .new files. So these are just multi-column files that you can use, can be plotted with the new plot or other plotting programs. Then there is this seek.out, and this contains the final value for the parameters and other information. I will show you later. Now, hopefully, this does not take too much to load. Maybe it's, wait. I will show you through, I will show you through my computer, which is faster. So, yes, okay. So I think you see this one, no, on your, if you do it. So if you do TDPS, you should see this window. So these bars are, let's say, the estimated noise in various interval of your experimental data. And then this dashed line is, how to say, the estimated standard deviation using weight 1. So in general, you should use a weight that follow this noise distribution. So if your noise distribution is flat, you should use 0. If it's more, how to say, more decreasing, let's say, in intensity, then you should use higher weights, 2 or 3. So this is one way to decide. Yeah, okay. So this is, yeah, this is, as you can see, this is the PE, so it's the fit. So you see in blue is the experimental data, and in green is the fitted signal. These, how to say, dotted lines are the energy range that we didn't fit because there are glitches. And so if you look at PA, there are various windows. Yeah, so this is the experimental data, this is the post-edge background. Then here there is, this is the edge energy that chosen by the program, and this is the jump. And then here we have the post-edge background, and you see here this is the multiple electron excitation that has been fit. So it has this this shape. And you see here again, yeah, this multiple electron excitation that we put. Then others, yeah, maybe you can see the Fourier Transform. Sorry, not this one. This one, yeah, after fitting. So again, experimental and the theory and the residual. Okay, let me go back to the server. Then, as I said, there is the .new file. This, if you look it inside, it's just so multi-column file. So we have K experimental data, the model, and the residual. So we can plot it with new plot, for example. So X is for the X-axis. So using 1, 2, and 1, 3. Okay, takes some time. Yeah, so I forgot. Let me do it line. So first, second column is experimental point, so I will do it points and then the fit with line. And then we can also plot the residual with line. Yeah, okay. So you see how red points are experimental data. Actually, the points where you see there are spikes in the residual because there are glitches in the data that we didn't fit. So we didn't consider. So this is it. And yeah, the output file so is the name that you have given. So in my case is cist.out. So if you plot it, there are various different information. There is the energy edge selected, okay, the slope, the white line. Then there is the jump, how much is your the signal, the spline coefficient for the post-edge background. Then there is this the R value, the residual, standard average standard deviation determined, and so on. And then we have the values of the various parameters that we fitted. So this is, you see the numbers is the same that we used in the table. So 15 was the distance. So this 2.021. Then this is the Debye-Waller, the angle, the thermal, the sigma square of the angle, the correlation, and so on. The E0, S0, and so on. So, yeah, and if you see the coordination number we kept fixed, so it remains at 4. So, okay. So, I quit it for. So, this is it for this tutorial. So, I don't know if you have any question. And if not, I will do small presentation about reverse Monte Carlo. Then maybe later we will see another GNXAS example, or maybe we will do a short reverse Monte Carlo tutorial.
I think there are some things in the discussion.
In the chat? Yeah, in the chat I answered before.
Okay, so then in
okay,
that case, I
yeah,
think here we do not have any, but is there, okay, so right now we don't have any other particular questions, Fabio. We can proceed with the presentation, I believe.
Okay, so...
So, which means we will have about half an hour for the presentation and then we will go
Yeah,
to
yeah.
the break.
The video doesn't work. Can I share screen? Probably means yeah. There is yeah. I think you can share. Can you share the screen so I can see the error?
Who?
One guy in
Discussion, you mean?
the Zoom.
In the discussion.
Yeah, yeah.
Okay,
yeah.
so let me see. The video doesn't work. Can I share screen? Oh yes.
Yeah, please. So I removed mine.
So you can Aditi, you can speak also. I think.
Remove the right arrow in the end. So yeah. Yeah, okay. That was the problem.
Okay, so.
Okay. So yeah, maybe I mean not everyone is familiar with the command line, but so basically the left arrow means the input file, and if you write the right arrow is the output. Usually the output appears on the terminal, but also you can do right arrow and some name file, and you can save the output in some file also. Okay. Let me open my presentation. Okay. So yeah, so I will briefly talk about reverse Monte Carlo. This is based on GNXAS, so I will explain briefly what is reverse Monte Carlo and why we decided to use it. So as we explained before now, so usually what we do is describe the pair distribution function, which is this quantity for a system using various peaks. This is called the peak fitting approach. So where these peaks depend on some parameter, and we refine this parameter against the experimental data. Now, of course, this works very well with crystals, because the shells, so the pair distribution function has clear peaks. So the first shell, second shell, the third shell, and so on. But if you look at disordered system, we have distribution function which are like this, which have some shells, but it's not clearly defined as in the crystal case. So how to fit this with the peak fitting approach? Well, actually for simple system, for monatomic and binary system, the peak fitting scheme can still be applied, but it's more, cumbersome. It's more difficult. You need additional information, and you need constraint to treat this in a correct way. Because the risk is that if you blindly apply the peak fitting approach to this to a disordered system, probably what usually happens is that you find very underestimated coordination number. This was shown, is clearly shown in one paper by Filipponi that I suggest you to read, which is also a nice summary. It's called GNXAS for liquids. It was done in 2000, so it's a review paper. And in that paper, there's also this example of, I think, amorphous germanium, where it shows that, if you apply the peak fitting approach without this additional constraint, the parameters that you obtain are completely wrong. So then, the problem is how we will treat these cases when we have more complex system, like maybe free atomic component system, or more, I'd say, complicated components where we don't know the additional information. And also, GNXAS is quite sensitive to short-range ordering, but it's not sensitive to long-range ordering. So we wanted also a method that should be able to refine, how to say, simultaneously both the short ranger and the long ranger to have a more correct structure. And also, we wanted model independent approach because, as I said before, we don't always know this additional information like the compressibility of the system, which is required for this peak fitting approach. So for this case, we used reverse Monte Carlo, which is a data analysis method that is based on structural modeling. So basically, you can think as reverse Monte Carlo as a typical simulation technique, like maybe, I don't know if you are familiar with Metropolis Monte Carlo. So Metropolis Monte Carlo, what you do is you start with a potential, and then you do Metropolis Monte Carlo simulation where the atoms are moved randomly to minimize this potential. Then at the end, the results you obtain, you can compare with some experiments or with some other data, and then you can, how to say, see if your initial model was correct. Instead, reverse Monte Carlo won't use the same idea, but we want to use the experimental data to move the structure. So to do that, what we do is that we use the experimental data, and then we apply the same Metropolis Monte Carlo algorithm, and in the end we obtain a configuration that minimize our experimental data, in the sense that the signal calculated from the computer cell is the same within statistical noise, of course, with the experimental data that we obtain. And so we can say that the configuration that we obtain is able to reproduce our experimental data. So in some sense, it's, of course, it's not the real structure, because it's not the real structure, but it's something that probably it's compatible, so it can be a possible structure, let's say. So, so for this, we developed an RMC code. Let me say, before I continue, that, okay, so reverse Monte Carlo was developed in the 1988 by Pusztai and McGreevy, and so initially it was used mainly for diffraction data, so they were refining the structure factor, but it can be used in principle for any experimental technique for which the experimental data can be calculated starting from the coordinates of your system. So in this case, can be also applied to GNXAS. So in our program, we refine both the GNXAS signal, but also the pair distribution function. We do this mainly to refine the long range order in our system, because this distribution function can be obtained, for example, by X-ray diffraction or by neutron diffraction. But the problem is that these are obtained by the Fourier transform of the structure factor. And what we obtain in this case is that usually the accuracy of this pair distribution function is not, let's say, it's not so accurate at shorter distance, but it represents very well the long range order constraint. So if we combine the two, given instead the high sensitivity of GNXAS as short distance, we take, how to say, the best of both techniques. So the quantity that we minimize in the simulation is the difference between the experimental EXAS signal and the same and the signal calculated from our computer simulation. And also we for the pair distribution function. In the case of multi-atomic system, we can also use the partial pair distribution function, which are the atomic specific distribution function, so for specific elements. And so this is the typical algorithm of the RMC. So we start initially from an initial configuration that can be guessed or can be created randomly. And in general, we have two different ways to create an initial configuration. We have, let's say, two different kind of system. We can have molecules where same replicas of the molecules is repeated many times, and the total signal is calculated as the average of the different molecules. This is to simulate thermal disorder by using replicas, or instead for I would say solid system, or let's say condensed systems, we have a given number of atoms in a cell with a periodic boundary condition. So in the case of molecules, it's just single molecules repeated many times in space but uncorrelated. While for condensed system is a given number of atoms in a given volume, and this volume is kept fixed. So one requirement is that we should know the experimental density of the system that we are studying, so that we can fix the correct density. Then from this initial configuration, we calculate the signals, the initial signals, and we calculate the initial residual. So for EXAS, we actually calculate only the two body. And to do this, we pre-calculate the two body signals for many distances. And then we interpolate this on the actual distances inside the system. This is just to speed up the calculation. Then, of course, we have this reduction factor. We have the sigma 0 square, which is kept fixed in RMC, and the experimental resolution. And also, usually for EXAS, we limited the calculation up to 6 or 7 angstrom, because again, EXAS is mainly short sensitive because of the mean free path. After this 6 angstrom, the EXAS signal becomes basically 0. So we can cut this the calculation at this distance and speed up the time. So after this initial configuration, what we do is that we take one atom and we move it at random with a given step. So after it's moved, we check with some constraint. For example, some typical constraint that is used is that a closest approach, in order that the atom does not overlap with each other. And also we can use some maximum distance constraint. This is to avoid that molecules becomes disintegrated, basically. After we move, and after we check these constraints are satisfied, we calculate the new signal and the residual. And if the residual is decreased, the new configuration is accepted. If it's instead it's not decreased, we can still accept it with an accepted reject probability, which is the same as the Metropolis algorithm. So with this the probability is given by the difference in the residual. And we repeat this process many times, basically, for all atoms and for many steps. And after we do this a number of times, in the end, we will have a configuration that fit our experimental data, basically. Okay, this is a partial distribution function. And yeah, one point is that the atomic displacement, so how much we move our atom, is modified after every steps to have an acceptance ratio of moves that is about 0.5. This is how to say, a thumb rule that we use in order to move the configuration. Okay, so
so in the loop, may I?
Yeah,
So
yeah, sure.
in the loop, once you, for example, let us take a configuration 1, C1. So once you set it up and then get inside, so I don't see any particular thermalization or something. Once you have a particular configuration, do you use some number of cycles for thermalizing or bringing the system for equilibrium?
Yeah. So basically, we move all the atoms in the configuration, but we do this for many steps. So initially, as you say, there is a thermalization process, but after a certain number of steps, we reach some minimum.
Yeah.
But then we can continue to run the simulation and then calculate the statistical quantities over this after thermalization. Yeah,
Okay.
exactly. So sometimes reverse Monte Carlo is criticized because they say it does not produce a unique model. So then some people say, it's not a unique model, so it's not correct. But the point is that RMC is not trying to understand what is the true or real structure, because we cannot know. But in a statistical sense, what we try to do is that to have a structure that is compatible with our experimental data, and by using also additional constraint with that, we can limit how much this structure moves, so we can get closer to this the true structure in a sense. So actually, reverse Monte Carlo tends to produce the most disordered structure because it's just random moves. So tends to create the most disordered structure that is consistent with the experimental data. So it's very unlikely that you find some feature present in the structure that are not given there by the constraints, because in the extreme case that you don't put anything to fit, you just have a disordered configuration. So if some order of feature appears, this is means that is driven there by the experimental data that you used as a constraint. So okay, this is like typical window when the program is running. So here in this case is silver bromide. So this is double edge fitting. So here we have silver edge, and this is chromium edge, and here you see the residual. So so I was saying before, so initially the residual will go down. There is like thermalization point until after a number of steps we reach a minimum, and then the configuration will move around that minimum. So what one usually do is that we run an initial step for reaching the minimum. Then after that, we run another simulation for a given number of steps and calculate the average quantities on this equilibrated configuration. And here you see the partial pair distribution. So in the case we have two atoms, we have three different partial distribution, because we have silver silver bromide, and bromide bromide. And then here we have the total one. Yeah.
So when you in the previous slide, as I understand, I mean in this slide itself, as I understand, it's for the multi-component system. Suppose if we have a system which is like manganese, iron, cobalt or so, which atomic radius are very closer. So there is also this idea of anti-site disorder, like atoms switching their position. So these kind of configurations are also involved in this initial configuration building in the reverse.
It depends how you construct the initial configuration, but the atoms are freely to move. So they can switch configuration. So
So for example, like in one particular unit cell, only one iron switches its position to cobalt and cobalt switches its position to iron. Mutual kind of anti-site switching that I'm talking about.
Yeah. But in this case, like if you use a crystal configuration as initial step, actually the configuration will move randomly. So unless it's a crystal, it will not remain a crystal. So in our group we mainly focus on disorder configuration. So RMC is more, let's say, adapt for that scope, but there are some other groups which instead focus on crystals, and I think in that case, well, first of all, for crystal, I mean, if you have to know more or less already what is the structure, and but I don't know if they do also this exchange. But in the case of disorder, these are really freely to move, so it does not matter if the initial position in the unit cell, they will move. So okay, so this is basically it. Now I will show you some examples of works that we have done with this. So the first one was a study of liquid and undercooled nickel. So here you can see here, this is the X-ray absorption, but as a function of the temperature. So we kept the energy fixed at one point, and we scanned the absorption. And this is for small nickel particles, and what you see is that by increasing the temperature, the absorption remains at the same level. The energy is at this point near the edge. And but when we reach the melting temperature for nickel, we see that there is a change in the absorption. And then if we cool down the system, actually the absorption remains around the level of the liquid phase. And this happens for up to 300 Kelvin below the melting temperature. This is known as undercooled phase. This was known since the 90s, this phenomenon that small metal particles could be undercooled well below the melting point. And then after reaching a critical temperature, then it solidifies again. So what we wanted to see is how the structure changed between the liquid and the undercooled liquid phase configuration for nickel, and to try to have some insight into the structure, because one hypothesis of why these metal droplets undercooled is that in the solid configuration nickel is FCC, and there was a theory in the 1952 by Frank that stated that maybe in the liquid configuration the most he said that the most favorable energy configuration by looking at energetic at the energy of various configuration by using l'energia potential, he showed that the most favorable configuration is the icosahedral configuration. And icosahedral have five-fold symmetry, which, as you know, is forbidden in crystals. So his hypothesis was that because icosahedral is the most favorable, maybe in the liquid there will be icosahedral configuration, and then when we need to crystallize, we would need to rearrange the atoms, but this requires some energy, so there will be an energy barrier to overcome before crystallization. So that's the reason of the undercooling phenomenon. So to study this, we performed the GNXAS experiments at these two different liquid phase, and here you see the GNXAS sigma, and you see they are quite similar in the liquid phase, of course, because it's very much disordered. But if you compare the there are some differences. And what we did is that we performed the reverse Monte Carlo on these two data, and we calculated the both angle distribution between nearest neighbors. So if you remember before the pair distribution function, if we consider the first peak, so this is the first peak that we obtained by RMC, and we calculated what is the angle between the atoms within this distance. So, and if you see the angles at this configuration where we have two clear peaks, one around 6 and one around 110 degrees, and these are compatible with the icosahedral configuration. And if you see the difference between the liquid phase and the undercooled phase, liquid phase is the red one and the blue one is undercooled. This 60 degrees peak is increased in the undercooled phase. So this is already an indication that icosahedral configuration is more present in the undercooled phase. So this could be the reason of the undercooling phenomenon. Then we also applied what is called common neighbors analysis, which is a way to probe various structure in the configuration. And what we saw is that configuration that corresponds to the distorted and defective icosahedra. This is this DCOS here called. And also configuration that instead corresponds to perfect icosahedra tends to increase in the undercooled phase, while the other configuration, which are more crystal-like, decrease in the undercooled configuration. So this icosahedral ordering tends to increase in the undercooled phase. So this is an hint that so the hypothesis by Frank was correct, that indeed the icosahedral configuration could be the reason of the undercooling phenomenon. Okay, then another cases that we studied was gas phase molecules. These were taken for various systems at the gas phase, so, and when possible also double edges were measured. So these are different kind of molecules with different configuration. So just to show you a few, for example, this is boron bromide free and gallium iodine free. So here you have in blue the experimental data, and in green the fit by RMC, and we see that the residual is flat, so the experimental data could be fitted quite well. And same here for other molecules. And what we obtain is that these are the pair distribution function for the various molecules compared with some electron diffraction measurements. Sometimes there is some difference in the height because the electron diffraction experiment were taken from the literature are sometimes at different temperature respect to our experiment of GNXAS. But the important point is that if we look at the both angle distribution for the central atom for all the molecules, in all cases we could obtain the correct angle distribution, the correct angle for the various molecules. And additionally, by calculating the average over different number of steps of the RMC simulation, we could calculate the average distance and the Boy-Waller factor, but also the correlations between the angles and the distances. And one important result is that this sorry, where is it? This correlation between the distance and the angle that basically gives you the direction of the vibration respect to the angle. So this, for almost all molecules, it's negative. So it means that when the angle decreases, the distances increases and vice versa. So there is a negative correlation between the distance, the neighboring distances, and the angle of the molecule. And last one, okay, this is another one. This is just an alloy of indium tin 4. This was studied because there was a paper published that saw some structural transition in this system at around 500 centigrades. So we repeated the experiment, but as you can see from the GNXAS, we didn't see much differences. And also we did RMC, so using the various super distribution function and the angles, but we didn't see any change in the structure that was published before. So, and then later there were other papers that confirmed that okay, this transition actually does not occur. So maybe there was some problem in the original paper with the experiment. Okay. So okay, I can conclude here. This is some of the references of the works that I showed here, and maybe later we can do the hands-on on the RMC. So also RMC, like GNXAS, has various programs that I use to create the structure, the DAR files for the calculation, and also program for the estimate noise on the experimental data, and then finally we run the RMC. Then after the final configuration, we have also some program for analyze to obtain the parameter, like I showed you in the case of molecules, but I think we will not have time for this. So for now, I conclude. I think now we do 30 minutes break, and then we start again at I don't know what time is in Europe, but
we'll start again. Okay, so let us thank the speaker for this session. And,
so
any questions? Okay, so let us bring it on during the hands-on session then. So okay, so we will have about half an hour break, and then we will get back to you. So I'll leave the system open. So during that time, the online users, if they have any questions or discussions, you can carry on as well. So it's open. So please, put on your questions and then discuss with Fabio.
Yeah.
Okay, so we'll be back in half an hour then. Okay.